Good afternoon, everybody. Welcome back to E304. Today we're going to talk about atoms and oscillations. So in the previous lecture we talked a lot about cantilevers and beams, and now we're going to talk about the interactions between atoms. So we're going to focus on a pair of atoms that are bonded together as a molecule, and we're going to restrict their motion only in the x-axis. So if we have two atoms and their electron clouds here, and these atoms have some separation between them, x, okay, and we'll assume that they can get closer together and farther apart, but only in the x direction. So this we're going to treat as a simple, undamped simple harmonic oscillator, like we discussed before. So simple harmonic oscillator. So balls on springs, essentially. So we have two masses connected to a spring, connected to each other via a spring. All right, so let's recall from the past chapter the Lennard-Jones potential. And it turns out that this is a useful way to look at this interaction as well. So Lennard-Jones potential, and we use it here to model the potential energy, PE, of these two atoms that are interacting. And the Lennard-Jones curves are not just applicable to van der Waals forces, although we use them for those, but the shape of the curve is common to really nearly all types of bonds. So just keep that in mind. So potential energy, and we'll have x in direction of the x-axis. So we might remember that in the Lennard-Jones approximation that we saw before, there was some separation xe, and the potential curve looked something like this, and there was a minimum there at xe, and then it came up like this and approached 0. So this equilibrium distance, this is sort of equivalent to our x is equal to 0 neutral position of our spring, if you will, in the approximation that we've seen before. All right, so over here at as x gets very big, the atoms don't really feel each other, and you can see the potential energy between them is 0. So potential energy approaches 0, which means the atoms are not interacting, and there's really no connection between them. All right, so from the potential energy, we can derive force. So let's look at force. F of x is equal to the derivative of energy, so d potential energy with respect to x dx. Okay, so if we look at this this force, well, let's write down what the potential energy is first. So potential energy, we've seen this before, looks like C1 over x to the 12th power minus C2 over x to the 13th power. And of course, C1 and C2 are the strength of the attractive and repulsive interactions, and they vary according to the atoms. So if we then take the derivative and find f of x, we see that that's going to be equal to minus 12 C1 over x to the 13th plus, I'm sorry, I made a mistake here. This is x to the C2x to the 6th. minus 12c1 over x to the 13th plus 6c2 over x to the 7th power. Okay, so if we plot these things next to each other, so to speak, let's see if we draw two axes, and this is the x direction here and the x direction here. This is our potential energy, this is our force, and we know that we have some equilibrium separation xe here. So again, our potential energy looks like this, and our force looks like something like this. And please excuse my drawings here. You can look in your book to get a better idea of exactly what these curves look like. Okay, so the point is that in our spring approximation, this spot, of course, is xe, but it's also the spot where the spring is in its neutral position, or x is equal to 0 position. So if we zoom in here around this area, we'll see that the force is a straight line, and the slope of that line is going to be delta f and delta x here. The slope of that line gives us k, our spring constant, k, so is df dx. And we see that around that x is equal to 0, whether the spring is a little bit compressed or a little bit elongated, that's sort of a linear force in between those in that area, and our k is going to be df dx there. So we can make the approximation that f of x is approximately equal to minus kx, and we know this from our spring constant, or our force equation for a spring, minus kx, and in this case x is going to be x minus x equilibrium. Okay, so we're close to getting this approximation of two balls on a spring for our atoms. So let's look at one more thing, and that is the mass of these two atoms. So we said already that we have two atoms, so this is going to be atom of mass 1, and then perhaps we have a second atom of mass 2, and then we have some spring force on this one and some spring force on this one, so F spring, okay? Again, we're working with this two masses on a spring model. And what we need to reconcile is these two masses, right? So we can't just add them up. Instead, in a case like this, we use a reduced mass equation. And reduced mass, m sub r, is m1, m2 over m1 plus m2. And if you want to see the derivation of this, you can find it online. It's a fairly common derivation for reduced mass when we're using two objects that are acted upon by a central force. Okay, so now that we have this reduced mass that tells us how this system behaves, we have a few final equations that we get left with. Okay, so kinetic energy is equal to 1/2. We know mv squared, so we're going to use reduced mass, mr v squared. We have potential energy, and we use the Leonard-Jones potential there to look at that, and that's going to be equal to 1/2 k x minus xe squared, based on our previous slide derivation. And then we have the frequency, the natural or characteristic frequency of oscillation, and that's going to be 1 over 2 pi square root of k over that reduced mass mR. So there's our explanation of how two atoms oscillating together are very much like two masses on a spring, and they behave that way. We have the kinetic potential energy and the characteristic frequency of oscillation. So this is all well and good, but there's something a little bit surprising here. So I'm going to pose the question, well, okay, kinetic energy and potential energy based on this classical description here are continuous. Is that surprising? Can this be? Based on what we know about atoms and then the quantum mechanical description of things. And we will tackle that question in the next lecture.